Now, this is towards you, this is towards you. Both the bonds which are down are pointing towards you. And just behind this, there are two bonds here on the back side. On the back side here, this bond, which you cannot see from there. See this one. That is again pointing down. That is again pointing down. Okay. So these two are, this is the wedge bond, this is a dotted line. This is the wedge bond, this is the wedge bond, this is the dotted line. Okay. Now see, now I told you to observe from here. Observe from this side. Meaning, you have to look like this. See here. Observe it from the front. From the front. You can see only one bond here. One hydrogen you can see here. One hydrogen you can see here. And only one hydrogen you can see from here on this side. So the back carbon hydrogens are eclipsed by the front carbon hydrogens. And that is what is eclipsed conformation. Now suppose I rotate, so now look at this hydrogen and this hydrogen. The angle between these two hydrogens is 0. The angle between these two lines is 0. This is in a straight line. Now let me rotate this second carbon. Let me rotate the second carbon slightly. Look here. I rotated 60 degrees. This carbon, sorry, this hydrogen I have rotated. By rotating this C along this bond, I am rotating. Now it has come to 60 degrees. It has come to 60 degrees. And here, these hydrogens are maximum distance away from each other. This hydrogen and this hydrogen, they are maximum distance away. And that, now if you draw the figure, you can see all the 6 hydrogen atoms. Okay? You can see all the 6 hydrogen atoms from the front. I hope you can see it. Right? I don't know whether I'm holding it properly. Okay. So you can see the 6 hydrogen atoms from the front. See that? Now it is very clear. All the 6 hydrogen atoms are visible. And that, when you draw the figure, that is what is called, that is what is known as staggered conformation. Okay, so that is staggered conformation. Right? Now, in staggered conformation, the angle between these is 60 degrees. This is the first staggered conformation. Now let me rotate it again 60 degrees. See here. Again it forms the ecliptic conformation. Again 60 degrees. See, I'm rotating only the back carbon. 60 degrees. It has come to the next staggered conformation. Again 60. One more ecliptic conformation. Again 60. One more staggered conformation. And it comes to the original. Okay. Now what we have to do is draw the energy profile diagram of this process. I'll take my board and share it with you and draw the energy conformation of this. Now here is, oh my God. Drawing it's a bit difficult, looks like. Let me draw it. Yeah. Now, yeah. Okay. Lucky. Let's come. So this is this one is energy. Here we are plotting the energy, and here is a dihedral angle theta at 0 degree. 0 degree means the front hydrogen and the back hydrogen are one behind the other. Now see here, we are only looking at two hydrogen atoms. These two hydrogen, the relative angle between these two hydrogen only we are looking at in drawing this figure. Now see here, you know eclipse conformation is a maximum energy. So it has got at 0 degree, it's having maximum energy, we will put a maximum here. Now you rotate the back carbon by 60 degree. The back carbon will come here. Oh, sorry. Drawings are not in control sometimes. This one and this one. So my reference hydrogen will come to this 60 degree. And remember, this is most stable form. Stable means least energy. So 60 degree I got less energy. Then it comes here. Angle is 120. Again, we get the same staggered conformation. Okay. Then it comes here. At that time, it's again staggered. Then eclipsed. Then staggered. Then eclipsed. All eclipsed form have got same energy. Now connect them. Yes. You have only two energy levels. One and other. Second, sorry. This is the second energy level. Have the same energies. Okay. So this is the energy profile diagram of ethane molecule or conformation analysis of ethane. One sec, I'll just close the door. Yeah. So this is the conformation analysis of ethane molecule. So it has got only one maxima and one minima. It has got only one maximum and one minimum. Now, the conformation analysis of cyclohexane is the next one. Cyclohexane, it's not a planar molecule. It is not a planar molecule. If it is planar, the bond angle should have been 120. But it is not actually 120 because it's an sp3 carbon. And therefore, cyclohexane exists in chair form. Oh, how did I draw this chair? Drawing the chair is a tricky thing. Actually, this line and this line should be parallel. This line and this line should be parallel. And this line and this line has to be parallel. Then you will get a very clear cyclohexane molecule. What you have to do is you can draw 4 lines, straight lines of course, and then connect them like this. 1, 2, 3, 4, 3. So this is how you can draw a cyclohexane chair form. So once I draw the cyclohexane chair form, right here. I think my board I'm holding in my hand, so I'm not getting a control of the board. Okay, right. Okay, let me now here on each carbon. These are the up carbons. These carbons are the up carbons. 1, 2, 3. Okay. These are the up carbons. Remember, this carbon and this carbon are eclipsed from if you're looking from the front. Okay. Now the 3 hydrogens which are pointing up, 1, 2, 3, and the 3 hydrogens which are pointing down. These 6 hydrogens are called axial hydrogen. Okay. So the one which is pointing exactly up. Okay. These 6 are called axial hydrogen. And on each of these at 120 degree to this one, there is a second hydrogen. Here also 120 degree from here to the top. So if the hydrogen is up, the equatorial hydrogen, the other hydrogen will be down. And here the hydrogen is down, axial hydrogen is down, the equatorial will be up. Clear? And here, equatorial will be down. Here, equatorial will be up. Right? Now let us look at the axial and equatorial bonds. On the up carbon, look here. There is the up carbon. Up hydrogen, so up, up. I will put carbon here, hydrogen here. Up carbon, up hydrogen, axial. So up is axial. Down carbon, down hydrogen. So down, down. Again axial. Down is axial, up is axial. Then this is the up carbon. It's a down bond. Down means pointing downwards. See, this bond is looking down, not up. That's the meaning of down bond. So this on the up carbon, down bond is equatorial. On the down carbon, up bond is equatorial. This is how you can draw. This is how you can draw the structure of cyclohexane chair form. Okay. Now, chair form of cyclohexane. Chair form of cyclohexane can undergo a process known as chair flip. Chair flip. What is the meaning of chair flip? This carbon can come down. So you will get a figure something like this. And this carbon can go up. See this. So this process is known as chair flip. during the chair flip, if you have a chair flip on this carbon, now here it is up carbon, so this is axial. But look at the same carbon here. This is equatorial hydrogen. Look at the same carbon here. This hydrogen will come to the down. This hydrogen will come up. So the one which is axial in one form will be equatorial in the other form. Will be equatorial in the other form. So chair flip will result in conversion of axial bond equatorial, equatorial bond axial. Okay. Now this is so this is the most chair form is the most stable conformation of ethane molecule. Cyclohexane molecule. It has got also a conformation known as boat form. This is the boat form. Boat form is less stable than chair form because see these two hydrogens are very close to each other. These two hydrogens here are very close to each other and they repel each other. So this is less stable. The boat form is less stable than the chair form. Okay. So this is boat form is, and one more thing. Here you can see here this hydrogen, and this hydrogen. These are the axial hydrogens. They are very close to each other compared to equatorial hydrogens. They are very close to each other. And therefore, they have a repulsive force. This is what is called 1,3 diaxial interaction. What is the meaning of 1,3? If you count from this carbon to this carbon, this is 1, 2, 3. Okay, so that is what is called 1,3 diaxial interaction. Two axial bonds on one carbon and the alternate carbon. 1, 2, and third carbon is known as 1,3 diaxial interaction. That is not the case with equatorial bonds. Look at the equatorial bonds. This is one equatorial bond. This is next equatorial bond. No interaction. It's pointing like wings. Okay. So this is axial and equatorial bonds, and I have already told you equatorial bonds are more stable. Now, one methyl cyclohexane. One methyl cyclohexane. Suppose I got a methyl group here. This can undergo chair flip. This can undergo chair flip and form, see here, yes, this CH3 has come here. And now it has become axial. And this is equatorial. And see here, this is an axial bond pointing downwards, and here is the next axial bond, hydrogen. And here also there's a hydrogen. Now see here, there is an interaction. And not only that, you have a bulkier H here, CH3. So there will be more interaction with these two hydrogens. Okay, and therefore, at equilibrium, this form exists more percentage. So this is a stabler conformation. less stable here. Because, why? Because there is less 1,3 diaxial interaction, not less. 1,3 diaxial interaction is avoided between the hydrogen and the methyl groups. Therefore, eclipsed conformation is more stable than staggered conformation. So, in methyl cyclohexane, the which one? The eclipse, the methyl group will prefer to occupy the eclipsed bond, eclipsed position. Sorry, the methyl group will prefer to occupy the equatorial position. Sorry. Okay, methyl group will prefer to occupy the equatorial position rather than the axial one. So this is less stable and the equilibrium will be more shifted towards less. So this is briefly about conformational analysis of ethane and cyclohexane. Okay, so now that tomorrow we'll take up the remaining portion, that is geometric isomerism and optical isomerism. Thank you for joining me, but very sorry that I had to I had a disturbance in the class